Alrighty. Just gonna plan out my day here. First thing on the docket is the file attributes chapter, which I did some reading on yesterday. So yeah. So we got file finish, file attributes reading, file attributes exercises, and then at 5, I think it's 5, maybe it's 6. I think it's at 6 today. I have D&D. So I'll probably break at 5 for dinner. It is 10 to, would you say noon? Then we break noon to 1 for lunch. And then 1 to 5. I'll say 4. 1 to 4. Extended attributes. Extended attributes exercises. That's 4 hours. I might get in. I'll say start. Extended. And then we'll break at 4. Cause I gotta do some like housework. My kitchen, it just looks like craziness right now, so. Alright, that's the game plan. Got a bit of a late start today. I was gonna go to the gym this morning to do some climbing. But I was just like so exhausted. Wednesdays are marked my rest day, but I like to go into the climbing gym occasionally on my rest days just to have some fun. But today it was not gonna happen. All right, let's turn this music off. It's kind of in a Zelda mood this morning. Alright, it's been a while since I played it. I never played any of the Breath of the Wild. Yeah, I never played any of those, but the last Zelda I played was Ocarina of Time. Classic. Is my stream going on YouTube? Let me see, let me test it. Does that pick it up? No? Yeah. Okay, it's picking it up. Alright, looks like everything's going here. Alright, time to focus in on this chapter. Alright, file permissions. In this section, we describe the permission scheme applied to files and directories. Although we talk about permissions here mainly as they apply to regular files and directories, the rules that we describe apply to all file types, including devices, FIFOs, and Unix domain sockets. Furthermore, the systemv and POSIX interprocess communication objects, shared memory, semaphores, and message queues also have permission masks, and the rules that apply for these objects are similar to those for files. Similar but not the same, apparently. Let's see what it said the same. Is this a... yeah, okay. Permissions on regular files. As noted in section 15.1, the bottom 12 bits of the st mode field on on the stat structure define the permissions for a file. So you got 3 for each group: owner, group, and everyone else. So that's 9. And then you have, I think, an extra 4 bits. I don't know, 3 bits. Those are for set UID, set GID, and the sticky bit. The first 3 bits are special bits known as the set user ID, set group ID, and sticky bits, labeled U, G, and T respectively in figure 15.1. We say more about these. I'm curious, because I've seen this now multiple times. Why is the sticky bit in Unix labeled T or T? T comes from sticky. Well, sticky starts with an S, so T doesn't make sense. Sticky bit was introduced in early Unix to mean that programs' text code segment should be kept stuck in memory after execution. That's why. So subsequent runs would be faster. Yeah. So I knew that was a historical usage for it. I didn't know that's where the name came from. It makes total sense, though, if you think about it. Okay. Let's kill that. We say more about these bits in section 15.4.5. The remaining 9 bits form the mask defining the permissions that are granted to various categories of users accessing the file. The file permission mask divides the world into 3 categories: owner, also known as user. The permissions granted to the owner of the file. The term user is used by commands such as chmod, which uses the abbreviation U to refer to the permission category. Group, the permission granted to users who are members of the file's group. Can a file have more than one group? I don't think it can. Obviously from these bits it can't. Can a file have more than one group, similar to how a process can have multiple, say more than one group? Supplemental groups. Okay. Three permissions may be granted to each category: read, write, and execute. The file may be executed, i.e. the program or script. In order to execute a script file, e.g. bash, both read and execute permissions are required. The permissions and ownership of a file can be viewed using the command ls-l, as in the following example. In the above example, the file permissions displayed are rwx, remptyx, empty. The initial hyphen preceding this string indicates that the type of file is a regular file. To interpret this string, we break these 9 characters into a set of 3 characters, which respectively indicate whether read, write, and execute permissions are enabled. The first set indicates permissions for owner, which has read, write, and execute permissions enabled. The next set indicates permission for group, which has read and execute enabled but not write. Final set are permission for other, which doesn't have any permissions. The sys.stat.h header file defines constants that can be ANDed with stmode of the stat structure in order to check whether particular permission bits are set. These constants are also defined in the inclusion of fcntl.h, which provides which prototypes the open system call. These constants are shown in table 15.4. Alrighty. In addition to the constants shown in table 15.4, 3 constants are defined to equate to masks for all 3 permissions for each of the categories owner, group, and other. The header file in listing 15.3 declares a function file perm stir, which, given a file permission mask, returns a statically allocated string representation of that mask, the same style used by ls. Pew. If the FP special flag is set to the file perm stir flag argument, then the return string includes a set of set user ID, set group ID, and sticky bits again in style of ls. The implementation of file permission is employee function and program listing 15.1. Great. I don't really care. I mean, there's nothing like super magical about this. It's like, okay, we do a size of to get a size. Okay, great. We're including standard IO in the file perms header. File perms defines the file perms function. You give it the mode and flags, and it gives you back a char start. That's probably heap allocated, I imagine. Does SN printf heap allocate? Let's see. No, it's statically allocated here, which is bad because now you can't call this concurrently. But yeah, at least it avoids the allocation. So here, we use SN printf. We give it the statically allocated string and its size, and then we say %c for character for 3, 3, and 3. So it's 9 bits. So we say, hey, perm user, read user. If it's true, we do R. If it's not, we do this. Same thing with write. And then for execute, we have to include these special flags. So we say, if it's executed, if we have execution bit set, then there's going to be a few things going on here. Wait a minute. So this is if it's set, and this is if it's not set. If it is set, and both of them are set, then we say set it equal to lowercase s. If it's not set, wait a minute, why would, oh, it's a set UID. Okay, so if the execution bit is set and the set UID and sticky bit are set, why would we? Sorry, this is not, I'm confused here. What is FP special? I guess that's what I need to define. Man FP special. It's probably not going to come up, but I could just vim test.c. Yeah, I just dump this thing in here, and then write it out, and then go to definition. That doesn't show up. FP special is 1. Oh, this is just a pound define. That's why. Okay. So if the execution bit is set and we're printing the special stuff, then we say, okay, the set UID. If it's not set, then we do S. I don't get why capital T is not set. Let's ask ChatGPT. Is T for sticky bit mean that it is set with or without the execution bit? I thought it was with, but it seems to be without. according to this code. T sticky execute bit set. Okay. I would have thought it's the other way around, but this is correct. Okay. Maybe we ask ChatGPT, why is it capital for only the sticky bit? What is the history there? I would assume lowercase would be the single bit set. What you are saying uppercase is. Yeah, just intuitively, it doesn't really like. I understand that's the rules, but it just doesn't make sense to me. Okay. Permissions on directories. Directories have the same permission scheme as files. However, the three permissions are interpreted differently. Read the contents list of the file names of the directory may be listed, e.g. by ls. If experimenting to verify the operations of the directory, read permission bit. Be aware that some Linux distributions alias the ls command to include flags, e.g. -f, that require access to inode information for files in the directory, and this requires execute permissions on the directory. To ensure that we're using a unaltered ls, we can specify the full path, or you can do /ls. Yeah. Right. Files may be created in and removed from the directory. Note that it is not necessary to have any write permissions on the file itself in order to be able to delete it. Execute. Files within the directory may be accessed. Execute permissions on a directory sometimes called search permissions. When accessing a file, execute permission is required on all of the directories listed in the path name. I'm going to pause right here. I need to take a bio break real quick. Be right back. Gotcha here. When accessing a file, execute permission is required on all the directories listed in the path name. For example, reading the file home mtkx would require execution permission on /home mtk, as well as read permission on the file itself. If the current directory is home mtk sub 1, if we access the relative path name sub 2, then we need execution permission on home mtk and home mtk sub 2, but not on home or home. Read permission on a directory only lets us view the list of file names in the directory. We must have execute permission on the directory in order to access the contents of the inode information or files in the directory. Conversely, if we have execute permission on the directory but not read permission, then we can access the file in the directory if we know its name, but we can't list the contents of the file, of the directory. This is a simple and frequently used technique to control access to the contents of a public directory. To add or remove files in a directory, we need both execute and write permissions on the directory. Permission checking algorithm. The kernel checks the file permissions whenever we specify a path name in a system call that accesses a file or directory. When the path name given to the system call includes a directory prefix, then in addition to checking for the required permission on the file itself, the kernel also checks for execute permission on each of the directories in the prefix. Permission checks are made using the process's effective user ID, effective group ID, and supplementary group IDs. To be strictly accurate for file permission checks on Linux, the file system user and group IDs are used instead of the corresponding effective IDs as described in section 9.5. Once a file has been opened with open, no permission checking is performed, but by subsequent system calls that work with the return file descriptors such as read, write, fstat, fcntl, and mmap. So open is kind of like this permission check boundary for the kernel. Like, you got to get through open, and once you're through open, you can do whatever you want. You can read and write, as long as the open produced a file descriptor that's capable of doing those things. Like if you say open and it's like a read write request, well, if you don't have write permission, the open will fail. So there's no sense in doing those checks later because you already checked it during the open. Boop. Makes sense. Where's my mouse? Oh, there it is. Okay. The rules applied by the kernel when checking permissions are as follow. If the process is privileged, all access is granted. If the effective user ID or file system user ID of the process is the same as the user ID owner of the file, then access is granted according to the owner permissions of the file. For example, read access is granted to the owner of the read permission bit is turned on, and the file permission mask. Otherwise, read access is denied. If the effective group ID of the process or any of the process's supplementary group IDs matches the group ID group owner of the file, then access is granted according to the group permissions of the file. Otherwise, access is granted according to the other permissions of the file. In the kernel code above, or in the kernel code, the above tests are actually constructed so that the test to see whether a process is privileged is performed only if the process is not granted the permission it needs via one of the other tests. This is done to avoid unnecessary setting the ASU process accounting flag, which indicates that the process made use of superuser privileges. The checks against owner, group, and other permissions are done in order, and checking stops as soon as the applicable rule is found. This can have an unexpected consequence if, for example, the permissions for group exceed those of owner. The checks against owner group and other permissions are done in order, and checking stops as soon as the applicable rule is found. This can have an unexpected consequence if, for example, the permissions for a group exceed those of owner. Then the owner will actually have fewer permissions on the file than the members of the file's group, as illustrated by the following example. So we echo hello world into a.txt, then we ls on it, we get read write on owner and just read on everything else. We remove read write permission from the owner, so everyone else has read except for the owner. And we try catting it, we get permission denied. But if we su into AVR, list our groups, we have user, staff, teach, all that stuff. One of the groups is users. And we cat a.txt and we're able to cat it out. I mean, we don't even need to have the group because read permission was given to everyone. Similar remarks apply if other grants more permissions than owner or group. Since file permissions and ownership information are maintained within a file inode, all file names, links that reference the same inode share this information. What? I didn't know that. Since file permissions and ownership information are maintained within the file inode, all file names that refer to the same inode share this information. I did not know that. I'm going to highlight that. Linux 2.6 provides access control lists, which make it possible to define file permissions on a per user or per group basis. If a file has an ACL, then modified versions of the above algorithm is used. We describe ACLs in Chapter 17. Permission checking for privileged processes. Above, we said that if a process is privileged, all access is granted when checking permissions. We need to add one proviso to this statement. What is a proviso? I don't even know. Caveat, condition. Yeah. Couldn't you just say caveat? For a file that is not a directory, Linux grants execute permission to a privileged process only if that permission is granted to at least one of the permission categories for the file. I guess that's to avoid root executing something that shouldn't be, which is a really good idea. Something that was never intended to be executed gets executed by root just because it's root. On some other Unix implementations, a privileged process can execute a file even when no permission category grants execute permission. When accessing a directory, a privileged process is always granted execute search permissions. We can rephrase our description of a privileged process in terms of two Linux process capabilities, cap DAC read search and cap DAC override, section 39.2. A process with cap DAC read search capability always has the read permission for any type of file. It always has the read and execute permissions for a directory. Can always access files in a directory and read the list of files in a directory. A process with cap DAC override capability always has read and write permissions for any type of file, and also has execute permission if the file is a directory or if execute permission is granted to at least one of the permission categories for the file. Sorry, oops. What happened there? It's page 299. We're about to hit 300. Where is it? Here? 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 Nope. There we go. There you go. Checking file accessibility, access. As noted in section 15.4.3, that effective user and group IDs, as well as supplementary group IDs, are used to determine the permissions a process has when accessing a file. permissions the process has when accessing a file. It is also possible for a program, e.g. set user ID and set group ID program, to check file accessibility based on the real user and group IDs of the process. The access system call checks the accessibility of the file specified in path name based on a process's real and group IDs and supplementary group IDs. If path name is a symbolic link, access dereferences it. The mode argument is a bit mask consisting of one or more of the constants shown in table 15.5 or together. If all the permissions specified in the mode are granted on path name, then access returns 0. If at least one of the requested permissions is not available or an error occurred, then access returns -1. Okay. The time gap between a call to access and a subsequent operation on a file means that there is no guarantee that the information returned by access will still be true at the time of the later operation, no matter how brief the interval. This situation could lead to security holes in some application designs. Suppose, for example, that we have a set user ID root program that uses access to check that a file is accessible to the real user ID of the program, and if so, performs an operation on the file. The problem is that if the path name given to access is a symbolic link, and the malicious user managed to change the link so that it refers to a different file before the second step, then the set user ID root may end up operating on a file for which the real user ID does not have permission. This is an example of the type of time of check, time of use race condition described in section 38.6. For this reason, recommended practice is to avoid the use of access altogether. See, for example, so-and-so in the example just given, we can achieve this by temporarily changing the effective or file system user ID of the set user process, attempting the desired operation, open exec, and then checking the return value and error node to determine whether the operation failed because of the permission problems. The GNU C library provides an analogous non-standard function, effective UID access, or synonymously e-access, that checks file access permissions using the effective user ID of the process. Okay. Oh, sorry, forgot to skip ahead here. Set user ID, set group ID, and sticky bits. Yay, sticky bits. As well as the 9 bits used for owner group and other permission, the file permission mask contains 3 additional bits known as set user ID, set group ID, and sticky bit. We have already discussed the use of the set user ID and set group ID permission bits for creating privileged programs in section 9.3. The set group ID bit also serves 2 other purposes that we describe elsewhere: controlling the group ownership of new files created in a new directory mounted in a directory. Oh, sorry, I gotta reread this. My mind was wandering. We have already discussed the use of the set user ID and set group ID permission bits for creating privileged programs in section 9.3. The set group ID bit also serves 2 other purposes that we described elsewhere: controlling the group ownership of new files created in a directory mounted with no group ID option. Yeah, I remember that. And enabling mandatory locking on a file. In the remainder of this section, we'll limit our discussion to the use of the sticky bit. In older Unix implementations, the sticky bit was provided as a way of making commonly used programs run faster. If the sticky bit was set on a program file, then the first time the program was executed, a copy of the program text was saved in the swap area. Thus, it sticks in swap area and loads faster on subsequent executions. Modern Unix implementations have more sophisticated memory management systems, which have rendered this use of the sticky permission bit obsolete. The name of the constant for sticky permission bit shown in table 15.4 is IS_ISVTX, derives from an alternative name for the sticky bit, the saved text bit. In modern Unix implementation, including Linux, the sticky permission bit serves another quite different purpose. For directories, the sticky bit acts as the restricted deletion. Wait a minute. Yeah, restricted deletion flag. Setting this bit in a directory means that an unprivileged process can unlink RMDR and rename files in directory only if it has the right permission to the directory and owns either the file or the directory. A process with the cap fowner capability can bypass a later ownership check. This makes it possible to create a directory that is shared by many users who can each create and delete their own files in directory but can't delete files owned by other users. The sticky permission bit is commonly set on a temp directory for this reason. Boop. A file sticky permission bit is set via the chmod command, chmod plus t file, t for text section of the binary, or via the chmod system call. If a sticky bit for a file is set, ls-l shows a lowercase or uppercase letter T in the other execute permission field, depending on whether the other execute permission bit is on or off, as in the following. The process file mode creation mask. This is something I haven't touched on for a little while, so actually we'll get some information out of this. UMask. We now consider in more detail the permissions that are placed on newly created file directory. For new files, kernel uses the permission specified in the mode argument of open or create. For new directories, permissions are set according to the mode argument to make dir. However, these settings are modified by the file mode creation mask, also known as the UMask. The UMask is a process attribute that specifies which permission bits should always be turned off when new files or directories are created by a process. Often a process just uses the UMask it inherits from its parent shell. Is there like a UMask echo $UMask? Something like that? Env grep I UMask? No. Often a process just uses the UMask it inherits from its parent shell, with the usually desirable consequence that the user can control the UMask of programs executed from the shell using the shell built-in command UMask, which changes the UMask of the shell process. Where's the UMask stored? Has to be in the process somewhere, not in the environment. The initialization files for most shells set the default UMask to the octal value 022. This value specifies that write permission should always be turned off for group and other. Thus, assuming the mode argument in a call to open is 0666, read write permission for all users, which is typical, then new files are created with read and write permission for the owner and only read permission for everyone else. Correspondingly, assuming that the mode argument to mkdir is specified as 077, all permissions granted to all users. New directories are created with all permissions granted for owner and just read and execute permissions set for group and other. The UMask system call changes the process's UMask to the value specified in mask. So it's a system call that takes in a mask and it operates on the current process. So it must be like stored as part of the process or the task struct in the kernel somewhere. It's a system call that the process makes against itself, but it can change itself at any time. So it's just kind of like, hey, if I ever do an open where the result of the open would be a create of the file or directory, apply this UMask. The mask argument can be specified either as an octal number or by ORing together constants listed in the table 15.4. A call to UMask is always successful and returns the previous mask. Listing 15.5 illustrates the use of UMask in conjunction with open and mkdir. When we run this program, we see the following. entity umask requested file permissions, processes umask. Yeah, it just masks everything out. That's fine. Listing 15.5, we employ the mkdir and rmdir system calls to create and remove a directory, and the unlinked system call to remove a file. We described those system calls in chapter 18. So let's just review this real quick. We're just including a bunch of headers, defining a bunch of constants. We go into our main, we allocate or declare a file descriptor, a stat structure, and a mode. And then we set our umask to umask settings. It's guaranteed to succeed. And we say, hey, if group write, group execute, or other write or other execute are set, then unset them. And then we say, I'm going to open my file. My file is just called my file with read, create, and execl. What's execl? Man to open execl. Was it? excl. Ensure that this call creates the file. Exclusive, that's what it is. This file is specified in conjunction with create. A path always, and a path already exists, the open fails. Okay, it's like an exclusive create. I'm the exclusive creator of this file that I'm opening. You give it file perms, which is read user, write user, read group, write group. So we lose write group. That's the one that's the same in the two of them. And then we make the directory with directory privileges, which have read, write, execute user, and read, write, execute group, and read, write, execute. So it has 777. And then our mask would remove read, write, execute. Wait a minute, sorry. Write group, execute group, write other, execute other. Yeah, so it's just read on those two. umask 0 retrieves and clears the umask value. Can I say umask from the CLI like this? Like umask. Okay, so umask is one value for both files and dirs. And the 2, I believe, is what is 0, 022 and permission bits? I think it's read, right? Right. It's right. So it says unset right. Okay. So if I ls-la and I say in shell, how do I in one command create a file, a new file with the permission bits set to 777. Install. I never heard of that one, man. Install. I've never heard of install. Okay. Obviously, I've not done a bunch of package management stuff. Install m777 dev null test file. And then umask. Okay. why isn't I want a single command that is affected by umask, so I can demonstrate that umask is doing what I intend. Masking the bits off 777. What the? I mean, I could just do test file 2 here. Wait a minute, that's not right. Doesn't have the execution bit set. Alright, RM test star. Alright. I don't know of a way of doing it in one command to demonstrate umask, so you just have to use the syscalls. Okay, changing file permissions chmod and fchmod. The chmod and fchmod system calls change the permissions of a file. Pretty straightforward. The chmod system call changes the permissions of the file named and path name. If this argument is symbolic link, chmod changes the permissions of the file to which it refers, rather than the permissions of the link itself. A symbolic link always created with read-write execution permissions enabled for all users, and these permissions can't be changed. The permissions are ignored when dereferencing the link. The fchmod system call changes the permissions of the file referred to by the open file descriptor. The mode argument specifies the new permissions of the file either numerically or as a mask formed by ORing the permission bits listed 15.4. In order to change the permissions on a file, either the process must be privileged or its effective user ID must match the owner of the file. To be strictly accurate on Linux, for an unprivileged process, it's the process file system user ID rather than the effective user ID that must match the user ID of the file as described in section 9.5. To set the permissions on a file that only read permission is granted to all users, we could use the following call. Makes sense. In order to modify selected bits of the file permission, we first retrieve the existing permissions using stat, tweak the bits we want to change, and then use chmod to update the permissions. That's not atomic. The above is equivalent to the following command. In section 15.3.1, we noted that if a directory resides on ext2 system mounted with the OBSD groups option, or mounted with the OSysV group options, and the set group ID permission bit is turned on for the directory, then newly created files in the directory take its ownership from the parent directory, not the effective group ID of the creating process. It may be the case that the group ID of such a file doesn't match any of the group IDs of the creating process. For this reason, when an unprivileged process, one that doesn't have the cap fsetID capability, calls an unprivileged calls chmod or fchmod on a file whose group ID is not equal to the effective group ID or any of the supplementary group IDs of the process, the kernel clears the set group ID permission bit. This is a security measure designed to prevent the user from creating a set group ID program for a group in which they are not a member. The following shell commands show the attempted exploit that this measure prevents. So we mount grep test so we can see, okay, BSD groups are applied. Option is applied to our mount. And then we ls on test, and we see there's no set UID on that. Directory has GID root writable by anyone. Yeah. And then for list ID, I don't have that group. CD into tests, we copy from my home directory this program, copy some mischievous program here, and then we ls the program, and now it has the group root. Hey, it's the root group. But how do you tell that the GID was set for the directory? Because I don't see that here. Like this, like wouldn't you expect one of these to be S? Sorry. BSD groups. There's like a table somewhere. Here it is. Oh, this is the BSD thing, which means parent directory group ID is always used, whether set group ID is enabled or not. Okay. So BSD groups kind of suck. Because they allow you to like get permissions from the directory itself. Oops. Here it is. Okay. Does that make sense? So you copy in the mischievous program, it gets the root group, and now I can chmod the group to be a set group ID program. No, you can't, because the kernel prevents that. inode flags, ext2 extended file attributes. Some Linux file systems allow various inode flags to be set on files and directories. This feature is a non-standard Linux extension. The modern BSDs provide a similar feature to inode flags in the form of file flags set using ch flags and ch flags 2. The first Linux file system to support inode flags was ext2, and these flags are sometimes referred to as ext2 extended file attributes. Subsequently, support for inode flags has been added to other file systems, including BTRFS and so on. The range of inode flags supported varies somewhat across file systems. In order to use inode flags on RiserFS file systems, we must use the mount O adders option when mounting the file system. From the shell, inode flags can be set and viewed using the ch-adder and ls-adder commands as shown in the following example. So we ls-adder, let's try this. We'll say echo foo into test, and then we'll ls-adder test, and then we're going to say ch-adder plus a AI test sudo, and then ls-adder test. So there's a lot of flags here, a whole bunch of flags that I was unaware of, Within a program, inode flags can be retrieved and modified using the ioctl system call, as detailed shortly. Inode flags can be set on both regular files and directories. Most inode flags are intended for use with the regular files. Although some of them also or only have meaning for directories. Table 15.6 summarizes the range of available inode flags, showing the corresponding flag name defined in Linux FSH that is used from programs in ioctl calls, and the option letter that is used with the chatter command. Before Linux 2.6.19, the FS star constants shown in table 15.6 were not defined in Linux FSH. Instead, there was a set of file system specific header files that defined the file system specific constant names, all with the same value. Thus, ext2 had ext2 append fl defined, riser had riser fs append fl defined with the same value, and so on, since each of the header files defines the corresponding constants with the same value. On older systems that don't provide the definitions, it's possible to include any of the header files and use the file system specific names. Wow. I mean, these are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different values here. I guarantee there's more than that here. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. It looks like 22 different things. Let's do man ls adder. Ls adder lists the file attributes. See chatter for a description of the attributes and what they mean. See, it says ext2, 3, and 4, but this is a btrfs. What is the command to get? What is the command to get the file system type given a file path? I forget what that is. Stat test. And stat dash f gives you file system. So yeah, it's btrfs, but it still has ls adder stuff. Sorry, what was it doing? Man ls adder. Yeah, look at all these freaking flags here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's only 18. Missing 4. guessing some of them are BTRFS, Butterfs specific. Okay, let's look at them. So append only, enable file compression, dir sync, synchronous directory updates, immutable, journal data. So you can do data journaling on a file. No A time, no dump, no tail packing, secure deletion, synchronous file, treat as top level directory. File can be undeleted, not implemented. Okay. So we're getting more into file system specific things here. The various FS star flags and their meanings are as follows. FS append FL. This file can be opened for writing only if the append flag is specified, thus forcing all file updates to append to the end of the file. This flag could be used for a log file, for example, only privileged cap Linux immutable processes can set this flag. FS comper FL. Store the file on disk in a compressed format. This feature is not implemented as a standard part of any of the major native Linux file systems. There are packages that implement this feature on ext2 and 3. Given the low cost of disk storage, the CPU overhead involved in compression and decompression, the fact that compressing a file means that it is no longer a simple matter of randomly access the file's contents via lseek. The file compression is undesirable for many applications. FS dir sync FL, make directory updates, open path name ocreate, link, unlink, and mkdir synchronous. I thought they were already synchronous. Oh, synchronous in that they flush to disk. Is analogous to the synchronous file update mechanism described in section 13.3. As with synchronous file updates, there is a performance impact associated with synchronous directory updates. This setting can be applied only to directories. The ms dir sync mount flag described in section 14.8.1 provides similar functionality but on a per mount basis. FS immutable FL, make the file immutable. File data can't be updated, write, or truncate and metadata changes are prevented. Only privileged process can set this flag for a file. When this flag is set, even a privileged process can't change the file contents or metadata. Journal data FL, enable journaling of data. This flag is supported only on the ext3 and ext4 file systems. These file systems provide 3 levels of journaling: journal, ordered, and write back. All modes journal updates to file metadata, but the journal mode additionally journals updates to file data. On a file system that is journaling in ordered or write back mode, a privileged capsys resource process can enable journaling of data updates on a per file basis. And setting this flag mount manual page describes the difference between ordered and write back modes. No a time. Don't update the last access time field when the file is accessed. This eliminates the need to update a file's inode each time the file is accessed, thus improving IO performance. See description of the no at time flag. And I feel like you can do this in so many different places. You can do it in the mount flags, you can do it in open flags, and you can do it in the file attributes or the file extended attributes, the file system extended attributes, or file system flags. I think it's really what they are. They're file system inode flags. FS no dump FL, don't include this file in backups made using dump. The effect of this flag is dependent on the -H option described in the dump manual page. FS no tail, disable tail packing. This flag supported only on the Riser FS file system. It disables the Riser tail packing feature, which tries to pack small files and the final fragment of larger files into the same disk block as the file metadata. Tail packing can also be disabled for the entire Riser file system by mounting I don't care about Riser. Secure remove, delete the file securely. Intended purpose of this unimplemented feature is that when removed, a file is securely deleted, meaning that it is first overwritten to prevent a disk scanning program from reading or recreating it. The issue of truly secure deletion is rather complex. It can actually require multiple writes on magnetic media to securely erase previously recorded data. Sync, make file update synchronous. When applied to files, this flag causes writes to the file to be synchronous, as though the osync flag was specified on all opens of the file. When applied to a directory, this flag has the same effect as the synchronous directory updates flag described above. Top dir, this marks a directory for special treatment under the Orlov block allocation strategy. The Orlov strategy is a BSD-inspired modification of the exceeded block allocation strategy that tries to improve the chances that related files, e.g. files within a single directory, are placed close to each other on disk, which can improve disk seek times. Not applicable in modern day with SSDs. UNRM allow this file to be recovered, undeleted, if it is deleted. This feature is not implemented since it's possible to implement file recovery mechanisms outside the kernel. Generally, when inode flags are set on a directory, they are automatically inherited by new files and subdirectories created in that directory. There are exceptions to this rule. The fs dir sync change adder plus d flag can be applied only to a directory, is inherited only by subdirectories created in that directory. When the fs immutable fl change adder plus I flag is applied to a directory, is not inherited by files and subdirectories created within that directory, since the flag prevents new entries from being added to the directory. No duh. It's immutable. Within a program, inode flags can be received and modified using the octal fsIOC get flags and fsIOC set flags operations. These constants are defined in Linux fs.h. Following code shows how to enable fs no a time flag on the file referred to by the open file descriptor fd. So we have fd already. We have this adders integer. We call ioctal on the fd. Say I want to get flags, and I write it into the adder memory. And then we OR in the no a time, and then we call ioctal set flags. Obviously that's not atomic. It's read, modify, write, so not safe for concurrent use. In order to change the inode flags of a file, either the effective user ID of the process must match the user ID of the file, or the process must be privileged to be strictly accurate. On Linux, for an unprivileged process, it is the process's file system user ID rather than its effective user ID that must match the user ID of the file as described in section 9.5. Summary and exercises next. Okay. Summary. The stat system call retrieves information about file metadata, most of which is drawn from the file inode. This information includes file ownership, file permissions, and file timestamps. A program can update its last access time and last modification time using the utime and utime's various similar interfaces. Each file has an associated user ID, group ID, as well as permission bits. For permission purposes, file users are divided into three categories: owner, user, group, and other. 3 permissions may be granted to each category: read, write, execute. The same scheme is used with directories, although the permission bits have slightly different meanings. The chown and chmod system calls change the ownership and permissions of a file. The umask system call sets a mask of permission bits that are always turned off when the calling process creates a file. 3 additional permission bits are used for files and directories. These set user ID, the set group ID. Permission bits can be applied to program files to create processes that cause the executing process to gain privilege by assuming a different effective user or group identity, that of the file program. For directories residing on file systems mounted using the no group or sysv group option, the set group ID permission bit can be set can be used to control whether new files created in the directory inherit their group ID from the process's effective group ID or from the parent's group ID. When applied to directories, the sticky permission bit acts as the restricted deletion flag. I wonder if it has any effect. Does the sticky bit have any effect on regular files? No, just directories. Cool. That's all I need to know. I don't need historical context. inode flags control the various behaviors of files and directories. Although originally defined for ext2, these flags are now supported on several other file systems. Inode flags control the various behaviors of files and directories. Okay. So inode flags are kind of like file system, inode specific file system specific capabilities. All right. Good Lord, that's a lot of exercises. All right, let's get to it. Section 15.4 contains several statements about permissions required for various file system operations. Use shell commands or write programs to verify or answer the following. Removing all owner permissions from a file denies the file owner access, even though the group and others have access. Yeah. So we can verify that. I'm going to go mkdir into chapter 15. And then here, I'm just going to say 15-7-1 exercise.sh main function main and then up here we're going to call test A. We're going to run function test A. Here we say, hey, I'm going to echo create new file with we'll say 666. Yeah. So we say echo make their build, and then we say, hey, echo foobar into build test A 12-1-test A, and then chmod on 666. Oops. On build 12-1 test A, and then ls-la build 12-1 test A. Once we've done that, okay, that should be fine. Echo, we'll say remove ownership bits, change mod minus, I would say O minus A, build 12-1 test A. Let's go ahead and chmod plus X this thing, 15. Okay, it doesn't like that. Chmod, man chmod, Yeah, just ask AI here. Chmod to remove ownership perms. Remove all. I want to leave group and other perms intact. Just remove the owner perms. User perms. Oh, it's u equal. Okay. U equal. Let's go ahead and run. Looks good. Okay, and then I'm gonna do an echo here, echo here. Let me say D2 there. This should fail. Echo foobar baz quux into build 12.1 test A. Hello. What the hell? There's no reason why that should ever glitch out. What's this test? Oh, dot test. What the hell is this thing? Test file. RM test. Why can't I remove it? LSLAG test. Okay, I'm the owner. It's a regular file that I can read and write. Oh, it's because of the attributes. ls adder test, change adder test minus immutable. Sorry, change adder. Sorry, it needs to do like this. Minus test, like that. Sudo. And now I can RM test. ls adder test. Man, chatter. Move all adders. The operator plus causes selected attributes to be added to the existing minus causes them to be removed. So why would this cause AM? Maybe like that. ls adder, RM, test. There we go. Jesus Christ. Chapter 15. And then why was this thing freezing? Is it recursive? What the hell is going on here? There we go. Create a new file. Remove the ownership permissions. And then that should fail. And then if you try RM build 15 or 12, it's 12. Foreground, Vim 15. I don't know why I'm still in chapter 12 in my brain. 12. Say local test file, and then we'll say test file is equal to, actually not, let's use this, build 15 -1 test A. And then we'll just search for this. Oops. Correct 3 words? No. Correct 6 words? No. Correct 7 words. There we go. Place with $test file. There we go. Oh. Looks great. Why does this freeze? I wouldn't expect it to. I mean, I don't have the permissions to delete it. So it must be getting stuck here, but I would expect that to... Oh, it's asking me to remove write protected file. So basically I needed to do the -f here. Yep, cool. Alright, so test A is good. Let's do test B now. On a director with read permissions, but not execute permissions. So we can read, which means we can list the directory, but execute means that we can't search the directory. Is that what it means? The names of the files in the directory can be listed, but the files itself can't be accessed. Yeah. Regardless of the permissions set on them. Okay. Well, we're going to do something similar here. We're going to make a tester. Call this thing tester. We're going to blow away tester. We'll call this test B. Okay. And then we need to make dir -p $tester. And then we're going to say create new dir. So we make dir, and then we say, hey, I want to echo foo into $test dir /foo, and echo bar into bar. Oops. So we got some files in there, and then we're ls-lag on $test dir. And then let's go ahead and run that. Test B command not found because I forgot to rename this to test B. There we go. So we have 7, and then this will be 5 because it's 1, 2, 3. So 1, 2, 3. Sorry, 1, 2, 4. No, 1, 2, 3. 1, 2, 4. So 4 and 1 is 5. Yeah. Okay. So then we go into here. We're going to stay in here. On a directive, read permission but not execute permissions. The name of the files. So remove execute permission. So we change mod -x on tester. This should pass, which would be the ls-lag. So you can list everything. This should fail cat $tester/foo or bar. Actually, don't need bar here. Alright, let's run the test. Okay. Well, we don't want A on this. This should pass. We'll just say ls tester. Okay. Did that. What permissions are required on a parent directory and the file itself in order to create a new file? What permissions are required on the parent directory and the file itself in order to create a new file, open the file for reading, open the file for writing, and delete the file? Huh? Well, what permissions are required in the parent directory and the file itself in order to create a new file in the directory? Create a new file would be write permissions on the directory. open a file for reading. I think you need execute for that. Open a file for writing. Same thing. And delete a file. I think you need write. So let me just write that out. What we're going to do is cp chapter 13 makefile here. Then makefile. And we'll just do clean. Make clean. There we go. Huh? Okay. Vim 15-1-exercise.txt. Or can I just do exercises.txt? Find yeah, I did both. See chapter 15, we'll just say exercise, or we'll do .txt here. C, we're going to say create a new file, open a file for reading, open a file for writing, delete a file. So create a new file would be, it says what permissions are required on a parent directory in the file itself. Parent would be, to create a new file, you need to be able to write parent dir file. We'll say none. So you have to have a write permission. And then I think you need uh, 000 on test. I'm going to say write, which is 200 on test. So I give it write. It's just going to freak out saying I cannot list, but can I echo foo into test bar? No, because I also need one execute. The directory stuff I'm not good at, admittedly. So 7 works, right? RM. So read is the list. I don't think I need read and execute. Because so you got all. So if it change mod to just read, which would be 200 test, and try echoing into the new file, it's like, no, can't do that. If I do it to 100, I just have execute, I can't do it. But if I have 1 and 2, should be 300. Then I can. So I need write and execute. Write and X, file none. Open a file for reading. The parent you would need execute. The file you would have to have read. Okay. Okay, so I'm going to make dir test and then echo food to test bar. I'm going to go into test bar and I'm just going to set change, cd into test, and I'm just set this is open file for reading, change mod to 200 on bar. Oh no, sorry, 100. No. 400. There we go. So I have read on the file. And then the directory, I think I just need execute, which would be 100 on test. And then if I try to open for reading cat test bar, I can still do that. But if I tried to open it for reading, it's like, or writing, it's like, oh, wait a minute. Echo test bar, permission denied. Or if I did vim test bar, it's a read-only file. Great. Okay. Cool. So it needs execute and reading, open file for writing. I think you need execute and actually let's try removing execute on this. Change mod 000 test and try doing our cat. It's gonna say permission died, yeah. Okay, so now we want to open a file for writing. So I think I sudo -i or ls-la sudo ls-la test, and I have to say sudo change mod on test bar to be just write, which is 200. So I got 200 there. I can't cat out. Well, I need to let me try doing my echo now. Okay, change mod +x on test. Sorry, change mod wants to be 100 on test. And now I'll do my cat. Can't do that, but I can do my echo. Yep. So that would be execute and write. And deleting. I don't think I need any. None on this, but the parent dir I need to have write on. So if I look here, sudo ls-la on test. I'm going to say sudo change own to 000 on test bar. Confirm that applied. No, it didn't. Oh, I did change own, damn it. Change own to C0, sorry. And change mod. There we go. There we go. Okay. So no permissions on the file. And then on the directory, we're going to say change mod to 200 on test. And then, so I got write, can't list in there, sudo bang bang, but I can do rm test bar. No? Maybe I need write on the file itself to remove it. Sudo change mod write should be 200 on test bar. Sudo ls -la test. So I got write on directory and on the thing. Let's try doing my RM now. Still nothing. So I'm going to remove that write permission. And then I think I need write and execute maybe? Because RM still failing. So change mod to execute, which is 1, and write, which is 2. So it'd be 300 on test. RM test bar. Yep. So I need write and execute. Seems weird that I need both of those. Sudo echo bar or foo into test bar. Sudo change mod to 00 test bar. Sudo ls-la test bar. Test. Change mod to just 100 test. And then try doing the RM again. Permission to that. So I need write and execute. Okay, so I figured those out just through empirical testing. What permission is required on the source and target directory to rename a file? If the target file of a rename operation already exists, what permissions are required on that file? Probably write. Doesn't exist. Okay. How does setting the sticky permission bit of a directory affect renaming and deletion operations? Okay. Okay, then source. Okay. MV source bar into DST. So I'm gonna have to change mod to at least right, which would be 200 on source and destination. And then probably gonna need execute. I'll probably need read on source. Write and execute would be 1 and 2, which is 300 on source. And then we'll do 300 on destination as well. There we go. So we need to write and execute. I'm gonna do MV destination back to source. Sorry, destination bar to source. Source. Change mod to 000 source bar. Okay, and then I'm gonna try my MV. Sorry, MV to destination. So it's read and execute on both. Or sorry, write and execute. Yeah. So this is gonna be write and execute, write and execute. If it does already exist, the target file needs to have write. So move back to source, destination, source. Okay, that's correct. Source is bar. If I sudo echo into destination bar, and then sudo change mod to 000 destination bar. Sorry, of destination bar. Sudo ls-la dst and source. And then if I try doing the MV from source to destination, it will fail. Huh. You don't need any permissions. I thought you would need write. But it's not needed. Alright, let's check the exercise key on this one. So this is going to be 15.2. Okay, so okay, bam. I'm just gonna write that out. Okay. I'm gonna go up to here. Say 15-1. C. Just indent those. Go here. Say 15-2. And then MV 15.1 exercise txt to just exercises.txt. Sure. Go down here. Do you expect any of a file's 3 timestamps to be changed by the stat system call? If not, explain why. So the 3 are birth, no. We have 4 here. Access, maybe. Modified, no. Access modified change. We'll ask AI here. Explain the 3 timestamps, access, modified, changed. We can just stat exercises multiple times here and see that's not changing. Let's look that up. Oops. The stats call doesn't change any file timestamp since all it does is fetch information from the file inode. There is no last inode access timestamp. Exactly. 15-3. On a system running Linux 2.6, modify the program enlisting 15.1 stat.t.c so that the file timestamps are displayed in nanosecond accuracy. I don't really give a shit about doing that. The access system call checks permissions using the process's real and group IDs. Write a corresponding function that performs checks according to the process effective user group. So there's already a libc function for that. As noted in section 15.4.6, umask always sets the process umask and at the same time returns a copy of the old umask. How can we obtain a copy of the current process umask while leaving it unchanged with the 15.5 here? So it's a process umask. I think umask with the argument of negative, maybe. Let's see. We got a man up umask to umask here. Oops. It's a mode T. I don't know what a mode T is. Is there another system call here for reading the UMask that I forgot? Maybe. Got UMask. You can use UMask 0 to set the UMask to 0 and then read it, and then call UMask. So, UMask of old to set it back. The chmod arx file command enables read permissions for all categories of users. My brain is not focused here. Okay. Let's check 15.5 to make sure we got that correct. 15.4 was about the access. It said write a corresponding thing, but here it says the GNU C library provides just such a function. We already talked about that in the chapter. In order to do this, we must use two calls to UMask as follows. Yep, exactly what I thought. It's not thread safe. Yep, totally. 15.6, the chmod all can now read and execute file with this sticky bit, maybe? Command enables read permissions for all categories of user, and likewise enables execute permission for all categories of user if the file is a directory, or execute permission is enabled for any of the user categories for file as demonstrated in the following example. ls-ld dir file program. Get dir file program, and then chmod a plus rx Okay, write a program that uses stat and chmod commands to perform the equivalent. I'm not going to do that. I didn't know that was an option in chmod, but whatever. I'm not going to do it. Write a simple version of the chatter command, which modifies file inode flags. See the chatter1 man page for details of the chatter command line interface. You don't need to implement -r, -v, or -v options. Sorry. I'm not going to re-implement stuff just for the fun of it. Alright. That's chapter 15. Boom, readme. Chapter 15 is now done. We can go to chapter 16, which is extended attributes. Bam. We go under chapter 15, RMRF, source, destination, sudo. There we go. Good status. All right. Cool. Gets CIM finish chapter 15. And then give me 1 second here. I need to mask my screen for a second. What is this here? Yeah, live. All right. And then if we do T7 done. We are now 23% complete on the book. I doubt we're that far. I like doing it by page number, and we are 310 pages done. So we can say 310 is what percent of 1400? So that means it'd be 310 divided by 1400 times 100. We are 22.14%. Close. Alright, 16. Where are we at time-wise? 2 hours into the session, and our goal was to do all this by noon. And it's noon. Well, I mean, we're 7 minutes over, but I think it's a good time to break here for lunch, and then I'll come back at 1 to 4 to do the extended attributes reading and start on those exercises. Cool. All right. Yeah, I'll be back in about an hour or so here. Yeah.